sulfate, sulfur, magnesium, and secondary effects on recycled wastewater we'll talk about a little bit more. So I'm going to go a little bit deeper into the issue of salinity, because one of the big issues of low quality water, and we saw that quite a bit of the water that we're using in Israel for irrigation is low quality, is in terms of the salts in the water. And whether that's brackish water in the desert areas, that's groundwater that's not used for anything else, but it's extremely salty. Well, the numbers here are in terms of decisiemens per meter, electrical conductivity of the water, which is a measure of the general salinity. These are very high levels, and crops like dates and olives and vegetables, including peppers, are being irrigated with very high salinity waters. But even all the rest of the water that's used in Israel in general, which we saw was a majority of it is the recycled municipal wastewater, is also fairly high in salts. Depending on the crop and the location, as we're putting on water to supply irrigation needs, we're also putting on a whole lot of salt. And that can be tons of salt per hectare per year that we're adding and giving to our soils with the irrigation water. Now, just a real quick overview of a water balance and a salt balance to try to understand what happens when we irrigate with water that has salts in it. So as irrigators, we're concerned mostly with providing the water for transpiration and evaporation needs. Transpiration is our productive use of the water. Evaporation is non-productive, but sometimes inevitable use of the water. All the other fates of water are avoidable, and we can try to just make sure that they don't happen. When there's salts in the irrigation water, those salts come with the water to the roots where the water is taken up, and for the most part, the salts aren't. The vast most part. The vast majority of salts will accumulate at the root surfaces as water is taken up to be used for transpiration. And that's where they cause problems. They cause problems osmotically. They pretty quickly start to cause problems toxically, first at the roots themselves, and then as some of those salts do get into the plants. In order to maintain crop productivity, in spite of these salts that are coming with the irrigation water, you can't let them accumulate to too high of a level, and therefore you need to add more water for leaching those salts out of the system. If there's not rainwater, like in a lot of our desert areas, especially during our growing seasons, then that water has to come from more irrigation in order to wash those salts out. Just as an example from some experimental work, this is some work with bell peppers in the Arava region of extreme desert in a net house. And we evaluated two irrigation water qualities, lower salinity and a higher salinity, which is this very typical salinity that our farmers are using. And here in this graph, we see that when we combined we added different amounts of water seasonally with the two water qualities. When we had good quality water, we were able to reach a maximum or an optimum yield when we supplied that evapotranspiration needs, essentially, which is about 700 millimeters in this case. With a higher salinity water, we were able, in this case, to reach the fruit yields of the higher quality water, but at a cost of doubling the amount of water we were applying. And essentially, that means that 50% of the water we were using here was going towards leaching the salts out of the root zone. So let's talk about or think about this 50% leaching. If our farmers are succeeding in agriculture by putting on lots and lots of water, that water is going someplace. Now, that water is going someplace with salts in them, and that water is going someplace with all kinds of other potential contaminants. In this figure, we see 25 years of quality from a well that's downstream hydrologically from this area where there's intensive vegetable growing happening, mostly in the winter time. In that 25 years, we see an increase of salinity of 2.5 times of the water in that aquifer. And that maybe could have multiple explanations, but there's no explanation other than the leaching water from the agriculture that to explain the 4 times higher nitrates that are found in that groundwater over that time period. So our success in dry land agriculture with low quality water comes at a cost. It comes at a cost, for the most part, here in Israel for now, of probably not being sustainable, because that kind of contamination of our deep soils and groundwaters isn't something that we can keep up forever. So I want to take a look out into a more national scale perspective of looking at what happens when we have this situation that's unique a little bit for Israel, where on one hand we have very high efficiency in giving irrigation water. We've moved to drip irrigation, and we're using smart decisions for deciding how much to irrigate, meaning we're driving towards more and more efficient and less waste. And on the other hand, going into the utilization of unconventional water resources that starts with the saline and recycled wastewater that are high in salts, and more recently go to desalinated water sources. So we see 3 things happening over time. Into the 1980s, this complete movement towards pressurized irrigation in Israel, with no surface irrigation left at all for the last 30 years, at least 40 years. So with most of the irrigated land being sprinkled, being drip irrigated, and the rest being sprinkled, where the rest of the world today is still at about 75% surface irrigation. The second thing is the utilization of recycled wastewater, that from the 1980s into the 2010s, we've gone and reduced tremendously the amount of potable or fresh water we're using for irrigation at the expense of more and more use of recycled wastewater or brackish groundwater. And then the third thing that's happened in the last 12, 13, 14 years, since about 2007 with the first big desalination plant on the Mediterranean coast in Ashkelon, that we've seen more and more desalinated water come into our system. And I'm showing it here as a function of the salinity in this graph in terms of chlorides in effluent reservoirs around the country, comparing 2006 until 2016. It's a little hard to see, but the brown and reds are high salinity, over 250 milligrams per liter chloride. The green and blue are low salinity. In 2006, 65% of our effluents that were available for irrigation were above 250 milligrams per liter, and today less than 20%, so 80% being much better quality water. So what happens with the dynamics of these things that come together? I saw Eran Rave was in the room before. So to work that really came out of Eran's lab and that we published together, that we saw a series of things happening. So when we looked at this period where we had high efficiency together with the more and more wastewater effluent being used, and here we're using sodium in leaves of citrus trees from labs all around the country. It's a big data samples, hundreds per year from all over the country, and we see this trend of increasing salts in the leaves of the trees over time. Again, because of the combined high efficiency and lower quality water. But from 2007 until today, we've completely reversed that trend, as the salinity of the wastewater and therefore the effluent that's being used for irrigation has gone down. So 1990s to 2007, we see increased salinity in soil and in crops. And if you're more interested, find our papers and see more of this data, including increases of salts in the produce that we eat. but a full reversal of these trends, lowering salinity in soils, crops, and produce happening after the large-scale desalination became present in the country. I want to use the rest of my time to talk a little bit about tools for managing decision-making when quality is an issue. This is a model from Shani et al. That I was involved with developing, an analytical mechanistic model based on soil physical properties and salt balance and water and salt balance and plant response functions to be able to explain the response of plants in terms of transpiration as a function of its salinity. It's a steady state model, fairly simple to run, because all you really need are a few management parameters, irrigation quantity and water salinity, some biological parameters about the expected response to water and salinity of the crop in question, and some physical properties, mostly about the soil hydraulic parameters and climate parameter. We won't go too much into that. What I want to do is show how we've tried to make this accessible. So we've turned this model into an application, and the user can go in, choose a crop. We'll pick the peppers we were looking at before, choose the soil, change the parameters that are running the model if the user knows better than the library, and then solve the model for a matrix of irrigation amounts and water salinity. So here we're getting water production curves for yield, expected yield based on transpiration for different water qualities. Now we realize that farmers don't make decisions based on this kind of information. Farmers make decisions based on economics. So we added a coupled section where we have the economic terms, including cost of water, and including all the things we need to do to be able to calculate profit or loss based on the yield and based on the water that's being used. So now a user can come and get a profit response curve, and sometimes the optimum amounts aren't trivial and not obvious. And this kind of tool also lets the farmer do some kinds of looking at how sensitive we are, let's say to yield, or let's say to the price of the peppers, and what he expects can happen, and maybe he can use lower quality water and still make a profit in spite of the first prediction that we saw. For that, he can also go back, and a lot of our farmers are doing this, and considering in the Arava switching from peppers to, say, dates, which are more tolerant of salts. We see less of a response to salinity.
Can you start to wrap up?
I will. I'm almost done.
Okay.
And consideration of how much water to use at what cost of what salinity, including the capability of seeing how much he could afford, or it would be worth his while to what didn't work. So at any rate, this kind of tool can help a farmer make decisions. It can also help us do consideration of things like feasibility study of desalination instead of use of brackish water, and to see that we can justify current costs of desalination, at least for high value salt sensitive crops in Israel under current economic realities. So to take it home, what I want you to maybe remember, if you remember something from this talk, non-conventional water sources for irrigation, yes, they've enabled us to have agriculture in drylands in Israel, but they're probably not sustainable in the long run, and there's a lot of issues that need to be addressed if that's the direction we want to go. The utilization of water high in salts comes with this high agronomic and environmental and economic costs, and particularly not sustainable. Desalination does seem to be a tool for leveraging sustainable irrigated agriculture in dry areas as a direct replacement for saline water, and more importantly, as indirectly in recycled wastewater and improving the quality. We need more tools for decision makers. I gave you a little hint of one. It'd be nice to have more. I want to thank funders and collaborators and you for your time, and I apologize if I went over a little bit. Thank you.
Thank you very much, Alon. You really set the stage for some of the other talks we're going to hear, as some of the strategies that you pointed to will be taken up in greater detail in some of the other talks. The next talk will be given by Professor Pedro Berliner from the Blaustein Institutes for Desert Research here in Stable Care. And he will look at what is a natural source, but a natural source for which we have to find an effective way of harnessing it. So Pedro, the floor is yours.
Just a second.
You need to do share screen.
Yeah, this is what I did. And for some reason it disappeared. Just a second. Something went wrong here. I'm not sure why my screen disappeared.
Are you using one screen or two screens?
One screen. Do you see it now?
Not yet, no.
Sorry. Somehow the Zoom disappeared. Okay, here I am now.
Look at the bottom for the green share screen.
Yeah, no, this is what I don't see. I see myself, but I don't see the screen. Jack?
Put it on gallery view, maybe.
Look, I suggest maybe the next talker, I will solve this problem and I'll come in after him.
Okay, fine.
Okay.
Then we'll switch over to Dr. Roy Bernstein, also from the Blaustein Institutes for Desert Research, from the Zuckerberg Institute for Water Research. And Roy will talk about water as a source of nutrients. The focus is on the nutrients. Then also water.
Thank you very much. Can you please thank you. Okay, do you hear me and you see my screen?
Yes, we do. It's fine.
Excellent. Thank you very much. So our research, what I'm going to present here is our attempts to develop a near zero waste and resource recovery industrial wastewater treatment. It's a collaboration between three groups from BIDR and two groups from Germany. So Alon talked a lot about wastewater as a source for agriculture uses, but wastewater can be also today a source for nutrient, even for energy. And therefore, advanced wastewater treatment technology should, first of all, be less energy intensive, should also be able to recover the stored energy in the organic matter and also the nutrient. And in addition, it should generate less greenhouse gas to the environment, and if possible, to valorize the excess sludge that is being produced during the process. One technology that we are investigating is anaerobic membrane bioreactor. It's a technology that combines anaerobic digestion together with the physical separation of membrane. It's considered to be a low carbon footprint alternative, and it also produces biogas, so we can recover the energy. It produces high quality effluent, but with high nutrient concentration because the nutrients are not being consumed during the process or hardly being consumed. This allows us quite easily to recover the nutrient, for example, using microalgae cultivation. In addition, one alternative to valorize or recover the sludge is using hydrothermal carbonization for sludge management and treatment. So altogether, our overall goal to develop such a scheme to produce high effluent quality and recover most of the valuable inside the wastewater. Specifically, we wanted to treat industrial wastewater with relatively high total nitrogen concentrations. And very important under realistic operation condition, meaning using real wastewater and growing the algae under outdoor condition, using and during different season. And in the end, we wanted to do a mass balance to see how much we can recover from the nitrogen, phosphorus, and carbon, and also obviously water. So the scheme is as follows. We have the industrial feed wastewater that we take from a potato chip factory about an hour drive from Sde Boker. We bring it here, and it is being treated using anaerobic AnMBR. We collect the biogas, and we also take some of the sludge or the excess sludge, and we treat it using hydrothermal carbonization, and then we get hydrochar and the liquid phase out of this process. Then what you see in the dashed arrows, it's something that we are going to investigate. The full one are being investigated. So the biogas be converted to energy, which can produce heat. Then we can take it to the anaerobic AnMBR. And also CO2, which can be fed to the photobioreactor where we grow the microalgae. In the effluent, we need to recover the methane, which is dissolved also in the effluent. And then we can also produce energy in CO2. From the PBR, we took the microalgae, we harvested them, but using centrifuge, it's not very economical. We need to think about other alternatives. And then we took the biomass and also the effluent, and then we analyzed everything. This is a scheme of the general process, the anaerobic system, thermoregulator, microalgae growth, and also HTC. This is how the anaerobic looked like. It was a 15-liter high throughput, meaning we have different membranes, several membranes inside. We can test the membrane quality. Submerged inside, it is computer control, and we control the biogas, pH, temperature, all the variables in the system. This is how it looks like in reality in our lab. Here we have the reactor and everything is controlled, and we also recycle the biogas in order to sparge and minimize fouling. These are the process operation conditions for the reactor. Three important things. First of all, the HRT is relatively high, but this is typical for industrial wastewater. The flow, the flux through the membrane was again relatively low. If we consider critical flux as the flux that the maximum flux that can we operate before we foul the membrane heavily, then we use a third of that, and this is in order to maintain relatively low fouling. And we also applied spurging again in order to minimize fouling. We used commercial membrane this time, but in the past we also used, we investigated different membranes, but this is out of the scope of this talk. I hear somebody else talking, so it's... if we are looking at the performance of their anaerobic systems, so we measure different parameters every few days. So first of all, you can see that the TOC and the DOC were almost completely removed, and the effluent was relatively high quality effluent. In addition, the total nitrogen and phosphorus were hardly removed, and we have a stream of high concentration of total nitrogen and phosphate, and the nitrogen was mostly ammonium. Also, because Alon talked about salinity, we have a little bit high salinity, and it increased a little bit because we maintain the constant pH, so we needed to add some sodium hydroxide. And this is something to keep in mind in the future as well. We also collected the biogas, so we had typical performance of the biogas composition with relatively high methane, CO2. Occasionally, we had a high concentration of H2S, depending on the water quality that we got from the factory. When we had a reasonable biogas production rate. Overall, we are still running the system more than 3 years already. It is relatively stable. We had very low fouling due to very conservative process parameters, and we need to clean the membrane every few months. In addition, in this research, we also took some excess of the sludge, about 0.3, to maintain a very high solid retention time, and this was treated by HTC. I will not, and for the HTC, we can do different things. We can use it for agriculture, soil amendment, we can use it for energy. We are currently investigating that, and I'm not going to show the result for this. And we also use the liquid for microalgae growth. This was published in another paper. So the anaerobic was very successful in our opinion, and then we used the microalgae to extract the nutrient. We used 3 species, 2 of them, the names are not very important. What is important that we used 2 local ones, 2 species that were isolated in Israel, and 1 that was sent from Germany. So one are more heat tolerant, and the one is more, can work better probably under colder weather. We selected these species because they are relatively robust, they are fast growing, they are easy to cultivate, and we can also produce high value product out of some of them at least. We used the 2.5 liter PBR, and it was put inside the water bath in order to maintain temperature, to avoid or to minimize evaporation. And we tested them during 4 seasons in desert climate, in the spring, summer, fall, and winter. Just a little bit about the climate condition in our area. So you can see that, of course, during spring and summer, the temperature are higher. We have long daylight time and high irradiation. So we expect to have better growth during this time. So for the result of our microalgae cultivation, what you see here is the result that we obtained during fall. We did it for all other 3 seasons. I'm not going to present it, obviously. And what we did, we ran every season in 3 to 4 cycles. In every cycle, we measured the biomass growth, the TN, ammonium, and TP in the effluent. And we ran it for several days, but the calculation we made until the effluent had the concentration of the TM and the TP based on the Israeli standard for unlimited irrigation, based on the AnMBR committee. TP is less than 1 ppm, and TN is less than 20 ppm. And then we made our calculation for the productivity of the system. So what we could see, first of all, that the TP for all season, for all algae, was consumed very fast. After 2 days, we could not see any phosphate, regardless of the initial concentration of the phosphate that we had. The second thing is that TN was consumed slower, and based on the TN concentration, we determined the cycle for the calculation of the uptakes. And for the fall, it was approximately 3 days. Again, for all algae, it was relatively similar. Based on these graphs, we could calculate the biomass growth rate and biomass productivity and TN uptakes. So what we could find is the following. What you see here is the biomass productivity rate for the 3 species for the different seasons. First of all, as shown, obviously the summer had the highest biomass productivity. And as expected, the fall was relatively low, and in the winter it's even lower. However, spring and winter, although the climate conditions were very different, were very similar, and this was quite surprising. So we analyzed the water and we looked at the water characteristic, and what we saw that the TP concentration and the ratio between the TP and the TN was much less favorable for maltoalgae growth during the spring. So this explained the reason why during spring we thought it will be the best season. We had the worst, or not the worst, but not as good as we expected. And this emphasized the need to monitor all the parameters online all the time when we are working under real conditions. In addition, we saw that the microalgae that was isolated, this is the gray scale here, that was isolated in Germany performed less good as the two other one that was isolated in Israel. And this shows us that you can optimize the system by choosing the right microalgae. However, it did not perform better in winter. So might be that we can find another microalgae that can perform better in winter, and then we can optimize it also based on the microalgae. We measured the TN uptake rate and the TAN uptake rate, and also the phosphate uptake rate. And we saw similar results, obviously. So the summer was the best, the fall was a little bit less, winter and spring were very, very similar. And again, the one that was isolated in Germany performed less good during the summer than the other one, but not better during fall. Another important issue for relatively good results is the fact that we use sterile wastewater because we use a membrane. So bacteria and other things cannot pass. So we have relatively sterile effluent. And we took images of the microalgae in different seasons, and we saw that they always remain clean without any bacteria growth or any growth of other algae. We also had relatively low evaporation losses, even in the summer, only because we use this thermoregulating system. And we had a very, very high phosphorus recovery. Later, we did more advanced mass balance analysis. We're not going to the whole details here, but we looked at the TOC, TN, TP in the inlet stream, and we measured the composition of the effluent in the end, in the algae, in the hydrochar, in the liquid, in the solid. And altogether, this scheme enabled us to recover over 76% of the nitrogen, 60% of the carbon, which can be much higher if we consider also all the CO2 that we can produce and we can recover to the PBR, and above 90% of the phosphorus. So altogether, we can say that a very nice scheme for really near zero waste disposal we was able to establish. We had a very high TOC fraction removed using the anaerobic AnMBR. We could recover carbon using the hydrothermal carbonization. Here we need to investigate what can we further do with that. Most of the nutrients were recovered, especially the TP uptakes were very, very high. Effluent quality could be attained within 2 to 5 days, depending on the season. This can be obviously optimized by just changing the biomass concentration in the bioreactor. And mass balance analysis demonstrated a near complete carbon, nutrient, and biogas recovery. With that, I just want to thank the sponsor and our collaborators, especially Jonas and Amit, the two students that did most of the work. So thank you very much.
Thank you. Okay, we're going, as I said, we're going to have the questions at the end. And so if you have questions for Roi's talk, please write them in the chat and we'll bring them up. So we're going to go back now to the talk with Professor Pedro Beluna on runoff and strategies for runoff capture. Pedro, it's yours. You need to unmute. Okay, good. And then do screen share.
Something is wrong here. Oh, share. Okay, here we are. I'm sharing now.
Mm-hmm.
Okay. Jack, I'm hearing myself, which is rather unsettling.
You might have to mute one of your other devices. Not the one in the Zoom, something else.
What?
I'm saying that if you have any other devices on, you might need to mute them, but do not mute your Zoom. And that's the one you're using now. So go ahead.
Okay. No. Okay. Okay, now it seems to be okay. Well, I apologize for the technical issues. I will be talking about runoff. And look, there is an echo.
Try lowering the volume. That might help.
Sorry?
Try lowering your volume a little bit. That might help.
I cannot see anything on the screen.
Pedro, if you have the conference site open and the video running, you're going to hear it twice. I know that was an issue for people yesterday.
Yeah, but
So you should maybe just close the conference site if it happens to be open. That might solve the problem.
Yeah, I cannot see it here, and I'm afraid that if I leave here, okay, I'm hearing you now, okay? Okay, I'll just try to ignore myself. I would like to, and I will like to introduce my talk by having a close look at the picture you're seeing in front of you, which shows the bare, no, sorry, this doesn't work. Just a second. יש תיקו.
אז איפה הבראוזר שלך? תלך לבראוזר.
איזה בראוזר? לסגור?
איזה תסגור? אופס. איפה פיקס? לא.
אוקיי. רגע, איך אני עכשיו חוזר
למצגת? לא. תעלה פה למעלה בחץ. לא, למצגת. ותעשה השם. כן, עכשיו רק תוודא ששומעים אותך.
Do you hear me now?
Yes, we do.
Okay, sorry, now I can talk. Okay, I was going to say that I would like to introduce my topic by having a close look at the picture in front of you, which shows you more or less how the area in which we carried out our work looks. You can see a very bare landscape and meandering down below the green line, which is actually a dry riverbed in which there are trees. The precipitation in this area is rather low. This graph is not completely updated, but what it shows is that the average precipitation is low. There are high fluctuations, but by and large, these are very low amounts of precipitation. And this precipitation is obviously not enough in order to produce agricultural crops. What is surprising is that now and then, when you walk around the area in winter, you suddenly face this type of waterfalls, which are the result of runoff. How does this happen with such low rainfalls? Is that sometimes, as we see in this graph, we have very high intensity bursts. The blue lines here depict the actual rainfall intensity, and the red line indicates the generation of runoff. What is this runoff? Runoff is the fraction of the water that was not absorbed by the soil and flows by gravitation to the lower lying parts of the landscape. The green line is, in this case, when there are annuals, and you can see that the presence of very scarce vegetation is enough to decrease the runoff. But the volumes of runoff can be large depending on the area from which we are collecting the runoff. In this case, what you see in front of you is a reconstructed farm from the Byzantine area. And instead of leaving the water to flow to a waterfall, it is redirected to plots. And the plots fill from the highest level plot to the lower lying plot by series of dams. And the water is ponded and infiltrates them. What is not possible to see in this picture is that the average water depth here is 40 centimeters or 50 centimeters, which means that when you have got one runoff event, you can fill each plot with around 500 millimeters of water, which is usually enough for one crop, particularly if we're talking about trees. In this case, we have plots which are of the order of, I would say, 1/10 of a hectare to half an hectare. But we can as well imagine or develop systems which are smaller, in which we call them microcatchments. We have an area which generates the runoff, which is quite small. It's over the order of 100 square meters or less. And there's a pit in which we have got a tree. The runoff flows into this pit, and the tree is supposed to grow. These systems are easier to manage than the large ones because you've got less water. But there is an interesting relation between the area which generates the runoff and the runoff efficiency. Runoff efficiency is here defined as the volume of water generated by a given catchment divided by the volume of rainfall received by this catchment. And you can see that it can go from 1% or 2% up to 40 or 50%, depending on the size of the area. But not only does the size of the area affect the runoff efficiency, what we have is as well, the size of the area affects the frequency of runoff events. When there are small catchments, the frequency is high. That means you have a number of runoff events. When you've got a large catchment, usually low. When I'm talking low, I'm talking usually between 1 or 2 events a year. The efficiency of runoff generation we just saw is very high for small catchments and low for large catchments. However, the runoff volumes are obviously a result of the interaction between the efficiency and the size. And for small catchments, you've got usually small volumes. And for large catchments, you have large volumes. If we look now at the detail of a microcatchment, how it would look, we have just here the area which generates the runoff. It has to be gently sloping in order to make sure that the water flows into the pit, in which we can plant preferably a tree, even though something else could be planted as well. The pit depth is usually of the order of 10 centimeters. And the objective of the system is to try to avoid drainage as much as we can, but the water is lost by evaporation or transpiration. I'm coming back again to this schematic or an artist's view of microcatchment. And why am I using an artist's view? Basically because the system failed. We planted large areas with microcatchments and it didn't work. And we decided to investigate why it didn't happen and if we could do something to improve such a system, because it's very friendly for farmers. It's easy to implement. As you can see, the pits are smaller, around 2 or 3 meters by 3 meters. It's very shallow. The bunds can be done by soil. And this is very appropriate for places in which there's no other source of water. Incidentally, this is the whole approach is appropriate for areas in which there's no infrastructure, there's no pressurized water. And as you remember Alon Gal's talk, this type of approach was not even mentioned because it's not really important in Israel. Even though it was developed here 1,500 years ago, it is relevant more for areas in which these infrastructures, as they are available in Israel, are not present. What we did is we, in order to see what caused this dramatic lack of success of the microcatchment, and I had the impression that it had to do with the evaporation of water from the bare soil. And indeed, we carried out a trial in which we looked at how the depth of the pit affects the distribution of water. And you can see here we made pits of different depths, 30, 50, and 70 centimeters. And as you can see, for the deepest one, the capillary rise did not reach the surface. So essentially, the soil surface was dry and water was not lost from the pit, while the uppermost, which is 30 centimeters, you can see the wetted area, which is much larger than the original structure. And this obviously means that you have got a much larger evaporation rate. This is 30 centimeters. For 10 centimeters would have been worse. Obviously, as you can see on the right-hand side pictures, you can solve this by inserting some artificial rings, but this is not really very practical for a farmer's point of view. And what we suggested then, instead of having a traditional design that you see on the left-hand side, we would have a trench, which would be a relatively narrow trench, in which trees could we plant it. If we have such a trench, we hypothesized that we would have less radiation reaching the bottom of the trench. There would be a turbulent movement of the air would be attenuated, and therefore the evaporation from the bottom of the trench would be much lower. Here you can see how it looked when we started off. This is after a runoff event. This is not where we carried out our trial, but this is more or less how our trench looked. And you can see here a box, which is actually the system that measures runoff. The objectives of the trial I'm going to describe is here how these trenches are efficient in terms of storing runoff, compared to a conventional microcatchment. And we will use two water application frequencies based on what I told you previously, that you can, by selecting the size of the runoff generating area to the runoff receiving area, have more or less water, and you can have one or more flood events. This was carried out in the area which I just showed you. I would just add that the annual evapotranspiration is almost 2.5 meters for a precipitation of around, average precipitation of around 100 millimeters. We simulated runoff because we wanted to carry out a very well-controlled trial. We gave it similar amounts of rate, not exactly, because at one stage we had to stop our experiment during the second year. In one case, we applied one flood, and in the other, we had 4 simulated floods with what was supposed to be a quarter of the amount of water, which is a quarter cubic meter per tree. We measured the transpiration of the trees using a Grenier method. we estimated evapotranspiration by using neutron moderating techniques, and we carried out this trial on young olive trees because they are very important in arid zones. Here's a schematic description of the layout. On the left-hand side, you see the tree in the trench, and the vertical lines are access tubes for measuring with a neutron probe, which you see on the upper left. And on the right-hand side, this is the conventional microcatchment, again with a 10-centimeter pit. And we added, as I mentioned, the same amounts of water each year to both microcatchments and trenches. We measure the transpiration using the Grenier system, which basically measures the change in the temperature of the water which is flowing in the xylem of the tree as a result of heating having a heater which heats the water, and we measure the temperature difference between the heated and the non-heated water. And the moment that this is proportional to the temperature difference, the maximum temperature difference and the actual temperature difference we measure. And if you look at the right, at the insert on the right, you can see a cross-sectional, a typical cross-section area of any tree, and you can see the probe. The probe is actually is a 20 millimeter probe, so it does not sample the whole of the xylem. Actually, we do not know what happens in the trunk. What is the actual area which conducts and what is the area that doesn't conduct. And one of the ways of doing it, you can do it by cutting the tree and doing a section of the tree, but then you cannot use your tree anymore. So what we did is we actually estimated the transpiration from the evapotranspiration data when we could assume that there was no evaporation from the soil surface anymore. And we decided that there was no effective evaporation from the soil when during a period of between 30 and 40 days, there was no change in the water content of the uppermost soil layer. We obtained this regression, which is quite good, and not always did our results conform to our requirement that there was no change. So we have not all the points, but only those that conformed. And we used this regression in order to estimate transpiration. Now to our results, this is for the first year where we applied only one flooding. And you can see the evapotranspiration is much higher for the microcatchment than for the trench during the first measurement period. And they do not differ that much thereafter, even though the evapotranspiration from the microcatchment is lower towards the end of the trial. The red line indicates the Class A evaporation pan, and as you can see, the evaporation rate from the pan is quite high. In this slide, I'm showing the transpiration is computed by volume divided by the cross-sectional area of the canopy. And what is interesting to note here is the different pattern. You can see the continuous line is the microcatchment, the stippled line is the trench. And what is interesting is that the transpiration from the trench practically did not change throughout the whole period. We're talking about around 120, 130 days after applying the flood, while in the microcatchments, the transpiration is dropping considerably, less than half. And again, we have the Class A evaporation pan as a reference. When we look at the second year, in which we applied always a quarter of a cube, and you can see here on the bottom in Roman letters 1, 2, 3, and 4, this correspond to the 4 periods. The first one is between the first and the second irrigation, the second and the third and the fourth. And the fourth period is a drying out period towards the end. You can see here as well that the evapotranspiration is higher for the microcatchment at the beginning, and the drop in the evapotranspiration for the trench decreases, but not at the same rate. If you look at the pan evaporation, it is not similar to the one that we saw for the previous year. There's no drop here. It was more or less a constant pan evaporation, but the rate is comparable. When we look at the transpiration again, we see that even though we've got here large standard deviations, and this is probably due to a problem related to the to how we estimate the cross-sectional area of the trunk, because we measure the perimeter of the trunk, but this does not mean that always the density of leaves is similar. But we see again what we saw for the previous water application, in the sense that the transpiration remains essentially constant, and the evapotranspiration, the transpiration for the microcatchment decreases, and decreases in this case quite dramatically, less than a quarter. We can calculate the actual evaporation rate from the data of evapotranspiration and transpiration, assuming that there is no drainage. This was the case for most of the trial period, with the exception for the first period during which we corrected for the drainage using the normal equations to compute drainage from hydraulic properties and assuming a unit gradient at the bottom. What you can see here is the evaporation rate was very different for the first measurement period, and was not that different throughout the rest of the first drying out period, and pretty similar at the end. For the second seasons, it is slightly different in the sense that the evaporation for the microcatchments is always higher than that of the trenches for the three measurement periods for which between irrigations, and both of them reach more or less zero towards the end. Because as I mentioned, having the cross-sectional area is a bit problematic, I decided to normalize it by the first measuring period, under the assumption that the canopy will not change that much during this 120 days, which are in any case after the rainy season, during which there is not that much leaf growth, or at least we do not observe that much leaf growth. And this confirms what I mentioned earlier, that basically the transpiration remains more or less constant for trenches and decreases for the microcatchment. From this, I think that we can summarize that the evaporative losses were higher for the conventional microcatchment. The transpiration of trees in the trenches were relatively constant throughout the trial. The transpiration rate was higher during the later phases of the trial in the trench system for both water applications, and it is reasonable to conclude that the direction in the reduction in direct evaporation losses is due to an increase in the water availability in the later parts of the trial due to the decrease in the evaporation. That's all. Thanks.
Pedro, thank you very much. As I said, people will be able to ask questions at the end. We're now going to hear the talk of Professor Amos Winter from the Gear Laboratory at MIT, and he will pick up on one of the themes that Dr. Bengal talked about in terms of the role of both desalination and application in drip irrigation for making efficient usage of water resources. Okay, so the floor is yours, Amos.
Great, thank you, Jack. It's a pleasure to be here today with everybody. I'm going to tell you a bit about our portfolio of work related to solar-powered electrodialysis, desalination, and drip irrigation, and how we've had to create a number of innovations to lower the cost of those technologies. My group, the Global Engineering and Research Lab, focuses on creating technologies for developing and emerging markets, and we often have to find ways to achieve similar levels of performance as we get in wealthier countries, but at a fraction of the cost. So to start out, just to give you a background of why we work on electrodialysis, our initial target country was actually India. We worked there for a long time. And the most prevalent contaminant of water in the country is salt. And this map shows the entire land area of India, and any color you see other than blue is salt that has, or is water that is too salty to safely drink. What compounds this issue in India is the lack of grid access. About 70% of the population of the country doesn't have, drinks groundwater as their primary water source. About 60% of the country still doesn't have reliable grid access. And about a quarter of the country's population lives in villages of 2,000 to 5,000 people. So, you know, this is more than 100 million people that both have brackish groundwater and don't really have viable access to grid electricity. So when we started working on this project, we obviously thought, oh, maybe solar could be a good energy option in this context. And actually, where you have the saltiest water in the country, you actually have the most solar irradiance. But we learned very quickly that commercial efforts, one by our partner, Tata Projects, to make solar-powered reverse osmosis systems were not successful because they were just too expensive because of the cost of the solar power system. So doing this detective work, we realized that actually electrodialysis could be a lot more suitable for this context than reverse osmosis for two primary reasons. The first is that if you look at the salinity ranges you typically find in India, around 1,000 to 2,000 parts per million or milligrams per liter of salt, small scale reverse osmosis systems require about twice the specific energy as electrodialysis systems. And so that means if you can go off grid with an electrodialysis system, you can cut the cost of your power system by about in half. The second compelling reason ED has an advantage is that current small scale RO systems waste about 60% of the water that come into them, whereas you can create small scale ED systems that waste only about 10% of the water. So you can better preserve the constrained groundwater resources faced by these rural communities. So because we put together this detective case, we found that there was a compelling reason for photovoltaic powered electrodialysis, not only in India, but really in many regions around the world where you have water stress, brackish groundwater, and where there's an advantage to use renewables. So following on that work, we started making full-scale systems, and our first was for a prize program for USAID, the DCEL prize, which we ended up winning. And then we've done a series of other field pilots, one that Jack Gilron was very helpful in Gaza. And what we've learned from those is a deep understanding of why we need to reduce the cost of this technology to make it adoptable on a large scale. So to put this in reference, our first system was about 60 grand. The stack was about $40,000. And to put that in comparison, a small scale RO system at the same production volume would be about $5,700. So somehow we had to close this price gap through innovation. So we did that by going into the fundamentals of how ED works and how we can manipulate it. So if you're not familiar with electrodialysis, the way the system works is you have a stack of ion exchange membranes over which you apply a voltage between an anode and cathode. You feed saline water between the membranes. The ions get drawn either to the anode or cathode, depending on their charge, and they can pass through at most one membrane before they're blocked. So this creates alternating channels of diluate, your product water, and concentrate, your waste brine. Now, another important concept in ED behavior is current density. So as you're applying this voltage over your membranes, you're going to drive a current through those membranes, and that current's going to be spread over an area. And that's your current density. And there's a limit to how much current density you can run through an ED system before you start splitting water and moving like hydroxide ions instead of salt ions. So we took these insights and thought about how does a typical ED batch system operate. So in a batch system, you'll start at a certain input salinity, and you'll circulate the water through the ED stack until you get to the product salinity. In this case, it would be 100 milligrams per liter. And if you run a traditional batch system with a constant voltage applied over the ED stack, you'll start at some starting limiting current or applied current density, and that'll actually drop over time as your salinity and your diluent streams goes down. And you set your voltage to never exceed the limiting current density. But what we realized is, we're wasting capacity of the system. In the beginning of the batch, we could actually run at much higher current densities, closer to limiting. So ideally, we could run very close to limiting current density throughout the batch and best utilize our membrane area and maximize our salt extraction rate. So we created a control system where we use a feed-forward controller, where we're always measuring the concentration in the diluent tank and the concentrate tank, and feeding that into an algorithm to adjust the voltage applied over the electrodialysis stack in order to maintain our current density as close to limiting as possible. And we're exploiting this phenomena of we're trying to increase our current density by changing our current, and we're doing that by changing our voltage to change the current, because the ED stack just obeys Ohm's law, V equals IR. So we've created these systems and made them in real life and experimentally tested them. And this is a small scale setup that we made a few years ago. And these are data showing different safety factors compared to the limiting current density. So VR equals 0.6 means that we're running at 0.6 the limiting current density. And this system was easily able to run at more than an 80% recovery ratio. And what we found is that compared to constant voltage, we could operate at a much higher production rate, or for the same production rate at a much lower area. So the punchline of this story is that with this innovation, we could either half our or double our production rate or half our membrane area, which basically halves the cost of the ED stack. So we could get the same performance as a normal system, but for about half the capital cost. So that was a major cost reduction innovation. The second big innovation we've created is time variant ED operation. So how you typically run an ED constant voltage system in batch operation is with a series of batches throughout the day. So this sawtooth pattern is showing the power consumption through different batches, and each tooth is a batch that you run throughout the day. And you capture energy in the middle of the day, and so you can run in the evening hours to maximize the utility of that energy. Now, what we realize is that the bell curve of the rise and fall of the sun is a very different power profile than this typical batch operation. And we hypothesized that we could actually vary our power consumption throughout the day to actually change it in sync with the rise and fall of the sun. So we'd run at high power in the middle of the day and lower power at the end of the day. And so we created a control system as well as an experimental setup that can actively manipulate the power throughout the day. And what we're doing is we're really taking advantage of the behavior of ED in that it has two primary independent variables that we can manipulate to change our overall power consumption. So the power consumption of the ED stack itself is proportional to the voltage applied squared, and the pumping power is proportional to the flow rate cubed. So these are two very sensitive variables that we can manipulate throughout the day in order to make sure the sum of ED power and pumping power always equates to our available solar power. And at every point of available power, there is a unique solution to voltage and flow rate to maximize our desalination rate. And so these are experimental data showing an actual system operating. And so our time variant system is in dark gray here, which is following the green bell curve. A conventional constant voltage batch system is in this light gray. And the state of battery charge for our time variant system is down here in the darker red dotted line, versus for the constant system, here's the state of charge throughout the day. We charge in the middle of the day and discharge at the end of the day. And so we need a lot more battery capacity. So we've thus far done some preliminary trials. We're going to do longer trials when we can travel again after COVID. But in our 6 days of experiments, we've shown that this technology can directly utilize our solar energy, 67% of our solar energy, versus only 40% in constant operation, because you always have to put some in a battery and then take it out after to run at night. We can reduce our battery volume or battery capacity needed by 92% compared to constant operation. And then we can increase our desalination rate by 54% compared to constant operation. So big, big advantages. And what this boils down to in terms of my overview of this presentation of reducing costs is all of these innovations together can enable us to drastically reduce the cost of a PV-ED system. So this is showing levelized cost of water composed of all the major cost components. And this is a full optimized time varying system if we have an operator operating it for 8 hours a day. But the operator cost is actually one of the most sensitive variables in the system. So there's no reason we can't just do an automated system. And this is then compared to a traditional Indian on-grid RO system. And our partner Tata Projects has done over 3,000 of these throughout the country. And the important takeaway here is that we're just about at price parity with a conventional on-grid RO system with our off-grid time-varying ED system. And that includes the large capital costs of the power system, but still overall, we're saving in energy costs and operator costs. So we're quite excited about that, meeting that price parity. Now, the other side of our work that I want to talk about is focused on drip irrigation. So the reason we're focusing on this is that throughout the developing world, there's, oops, my presentation is frozen for some reason. Let me just jump out of that and restart it. There we go. Throughout the developing world, there's about 2.5 billion people who live on small farms, less than 2 hectares. And in water-constrained countries like India, or certainly places throughout the Middle East, water consumption due to agriculture is a big issue. So already India in the next 10 years is projected to exceed its replenishment rate because of overusage of water. And already worldwide, 70% of water is used for agriculture. So in arid regions, you can't just take tens to hundreds of millions of farmers and have them start flooding their fields without over-consuming water available in groundwater. So the potential ideal solution, as Israel has figured out about 40 years ago, is drip irrigation, in that you can grow a lot more crops and use about 60% less water than traditional flood irrigation practices. And as far as the total market potential for growth, drip irrigation is still a small fraction of not only the total irrigated land in the world, but an even smaller fraction of the total cropland in the world. So what we're trying to do in my group is look at a traditional drip system where typically, geez, I'm sorry this keeps freezing. A typical drip emitter has to run at about 1 bar of pressure. And why that is a big barrier to entry for the small scale markets we're looking at in solar powered off-grid markets is it costs about $3,000 per acre to install one of these systems, mostly because of that power and pumping costs. So what we're trying to do in our group is lower the pumping pressure of drip emitters, which is the primary pressure drop in a drip system. And by doing so, we can lower the pumping power. Geez, I'm sorry, my presentation keeps freezing for some reason, but lower the pumping power by about half of the overall, an overall off-grid system. And if we could do this, we can both impact the lives of farmers in poor countries, as well as the lives of farmers throughout the world. Everybody can save money by lowering their pumping energy costs with lower pressure drip systems. So to do this, we would ideally use pressure compensated emitters so we can maintain a uniform flow throughout the field, which becomes even more important when you go to lower pressures. And we want to operate at about 0.1 bar. Historically, drip emitters, as I've said before, operate at about 1 bar of pressure. So we started by doing some reverse engineering and looking at how drip emitters are made and looking at the main flow control features as you open up an emitter and see what changes the flow to create this what's called pressure compensating effect, constant flow rate with variations in pressure. And what was interesting about this as we started to look into this is that this design is actually quite old. The first flow restrictors like this were invented in the mid-1940s, and they've been used, since then. But we realized that the theory that governs how they work had never been articulated quantitatively and predictively. So we had to investigate what the core flow control features were, which are the orifice, land, and channel. And then if we take two cross-sectional views of this emitter to give you more perspective, here's a schematic of what that emitter looks like, where there's a flexible silicon membrane, an orifice to drop the pressure as it goes underneath the membrane, lands over which the water flows, and then a channel which restricts the flow as the membrane deflects. So we were able to create fully parametric analytical models that govern both the deflection of the membrane and the fluid flow through the dripper in order to get a full picture of how this dripper behaves. Then we were able to put that into an optimization routine and optimize a new geometry for a dripper to operate at a much lower pressure to lower our pumping power. And so here are results of our first generation of emitters that have an activation pressure, which is the first pressure to deliver the desired flow rate, at about 0.15 bar, which is about 85% less than the normal industry level of about 1 bar. Now, why these results were so exciting is that we can reduce pumping energy in a drip system by about 50% with no behavior change. You swap out the drippers, you run your pumps at lower pressure, boom, you can cut your energy costs in half. And also for off-grid, our target markets, we can lower the cost of an off-grid solar-powered drip irrigation system by about 40%. So we haven't just done this in the lab, we've actually done 2 years now of field pilots throughout Jordan and Morocco at 9 locations. And in this study, we tested our emitters, which activated about 0.15 bar, versus conventional emitters made by Netafim and Adratec that operate between 0.5 and 1 bar. And we showed at these 9 locations an average of 43% reduction of pumping energy while maintaining industry norms of uniformity of water distribution. And in our second year of operation, taking out some user errors, we're actually operating near about 60% energy reduction. So farmers have been extremely excited about the cost savings they can get from these low pressure drippers. Now we're moving now into, and we've made great gains into making inline drip emitters. You're probably more familiar with these, where the flow control device is mounted within the pipe, and there's a series of flow control features to generate that pressure compensating effect. And it still uses a flexible membrane to do that. So we've been able to parametrically characterize these and again, optimize these. And here's a picture of one of our newest designs where we're operating less than half of the typical operating pressure as industry standard products. And here are a bunch of different products by different industry players. And not only are we able to operate at that very low pumping power, but also we can reduce the material required in the emitter by about 30%. And that's quite significant because these are commodity products and they're only sold for a fraction more than the material cost. So we're currently working with Toro actually on the next generation of these emitters. So what we're looking at now is what could we create if we combine our low pressure PVED systems with our low pressure drip irrigations technology to create very high value systems for farmers who can still operate off the grid if they need to or if they want to, just for lower cost or utilization of renewables. And there's a lot of compounding effects that add value in this scenario. So if we're talking about energy reduction, we can reduce energy using ED versus RO just because it's more energy efficient. And we can lower our required amount of energy substantially by using drip irrigation rather than like flood irrigation or sprinklers. So that cuts down our energy usage. Then we can further reduce our energy by using our low pressure drip emitters versus conventional emitters, which lowers your energy consumption by about 40%. And then in terms of water usage, we have 2 compounding beneficial factors as well. We can reduce our water usage with drip irrigation versus flood by about 60%. And then we can reduce our wastewater substantially using ED versus RO, which reduces the amount of water we have to take out of the ground and use in the system. So we get a massive fractional difference in reduction in our water usage. So we're currently now doing a large-scale feasibility study around the world of where are good target applications. So the USDA is interested in this because of the large swath of brackish water, particularly through the Great Plains. And also there's a lot of brackish water in the Central Valley of California. There's definitely applications in parts of the Middle East like Saudi Arabia. that have used desalinated irrigation water. And of course, Israel does that at a large scale. So also Egypt we've seen is compelling, in Australia. So we're working through the cost estimates and the detailed system design to really nail down what is the value proposition we can make to farmers. But we're pretty confident that we can hit levelized cost of water that's pretty similar or lower than other municipal systems like Israel, as well as the high value drip systems, and likely create integrated systems that are affordable and create value for farmers. So that ends my talk. And if you'd like to see more info about this work, you can go to gear.mit.edu and see our publications and descriptions of this research, as well as reach out to me directly at awinter@mit.edu. Thanks a lot for your time.
Thank you, Amos. It's a really interesting talk. I want to thank all the speakers. You can give an applause virtually with the sign on the bottom of the screen, so everybody can give their applauses. You can see it on the bottom. All four of the speakers gave really interesting and stimulating talks that I think opened up windows for all of us. There are a few questions that have already been asked, but if you have additional ones, you can either write them on the chat, or if you raise your hands, if I see you, then I'll have you do that. There was a question from Amos for Alon Bengal. Is the reason for the drop in the salinity content in both plants and drainage water solely attributable to the desalination, large-scale desalination? Alon.
I think that would be a little bit too large of a statement for me to possibly make, but it's certainly the most influential element in the changes that we're seeing. There's no other real explanations for why we would see salinity going down. And it seems to directly be connected to the reduced salinity in the wastewater, and then in the recycled wastewater, the effluent out following the desalination.
There's another question which I think either Alon or Pedro might want to address. What about tolerant rootstock genotypes, which would have ion excluding capacities? Would this allow exploiting more saline water resources without necessarily desalinating it?
I can address that only very limitedly. Saline tolerant rootstocks allow survival of plants under higher salinity. Often there's still reduction in production in spite of the tolerance, and there's certainly still the need for the leaching. So it at some level allows us to remain using the saltier water, or use even more salty water and have economic results. But with the other high costs that I talk about the contamination of soils and downstream waters, if that's groundwater or surface waters.
So it sounds like desalination it has more upsides than downsides at this point.
Maybe, and I know there's a session tomorrow where Alon Tal is talking about that in a policy and economic level. If people are interested, I think that would be an interesting talk.
Are there any more questions for any of the other speakers? I don't see any hands raised. I would like to ask one more to Amos. Amos, on the issue of variability of the solar radiation impacting the operation of the ED. Did you at all quantify or look at fluctuations that would be due to, say, passing clouds and variations during the day? And if so, what kinds of either price do you have to pay or advantages do you gain?
That's a great question, Jack, and I'm sorry I didn't get to go into more detail about how we deal with that. We actually use machine learning we take prior weather data sets from the location where we're operating, and we are doing constant projections in the future of what the expected weather is going to do. And so our current system runs on an hourly basis. Every hour, it's actually doing projections out for the full year forward and looking at its anticipated operating scenarios, inclusive of clouds and any other weather deviations, in order to ensure that it can meet its total production target. Because we can actually set the reliability of the production. We can do it day by day or year by year if we're hitting 100% or less than that. And there's some pretty big cost advantages to going from 100% to say 98% reliability in production targets. But yes, you are correct that we very much have to account for weather variation. And what's nice is that because the system can vary its power consumption so drastically, as I showed you, the pumping power is proportional to flow rate cubed, the ED power is proportional to voltage squared. So we're able to track like really crazy fluctuations throughout the whole day and still always be operating at our maximum production rate or desalination rate, really independent of what the weather throws at us.
Okay, thank you. Okay, I again want to thank all of the speakers. If you could again put up your applauses. I want to let everyone know that in another half hour, we will be doing a virtual water tour. And that tour will include some of the kinds of sites and some of the kinds of activities that were raised by the different speakers during our session. So for those of you that are interested, you can find that on the main site of the conference. I want to thank all of you for participating, and especially the speakers. It was a really interesting and stimulating session. And I wish everybody a productive participation during the rest of the conference. Have a good evening or a good morning,
Jack,
depending on where you are. Yes, Naftali.
there is also a food tour in half an hour, so we are competing.
Okay. So you have your choice of either going to food or going to water, and everybody finds their
We have
place.
a virtual restaurant in the conference.
Fantastic. Okay, again, thank you to everybody.